Hi, I'm Vincent, and I'm going to talk about our work, Bayesian Neural Network Priors Revisited. This was joint work with all these amazing people at all these great institutions, and it was motivated by the recent discovery of the cold posterior effect. So this says that if you take a Bayesian neural network posterior and introduce a temperature parameter, and then artificially decrease the temperature away from the true posterior to colder temperatures, you actually get a better performance. And so this is a bit puzzling since you would naturally assume the true base posterior to have the best performance. And in this paper, they suggested that this underfitting of the true posterior might be due to a misspecification of the prior. And so, in order to test this hypothesis, we took one step back and started looking at normal neural networks that were trained with stochastic gradient descent. And then we looked at the empirical distributions of their weights. So, what we found was that the weights of these networks, of these fully connected networks, were much more heavy tailed than a Gaussian. So that doesn't fit the general assumption of isotropic Gaussian priors that we often use in Bayesian neural networks. And indeed, they fit much better to a heavy tailed distribution like a Laplacian. And the same we actually find in convolutional neural networks. So that is one property that did not fit with the prior specification. Another thing that we found was that in convolutional networks, we often have correlations between weights. So especially if you look at the lower level convolutional filters, you often see positive correlations between neighboring pixels and negative correlations between faraway pixels. And so these two properties, the heavy-tailedness and the correlations, we tried to incorporate into Bayesian neural network priors. And we found that if you take fully connected Bayesian neural networks with these heavy-tailed priors, so for instance Laplacian or student T distributions, you get an improved performance and a reduced cold posterior effect. So you see that the difference between the true base posterior and the cold posterior is much smaller than in the case of the Gaussian, for instance. Similarly, in convolutional Bayesian neural networks, we also get a reduced cold posterior effect, but we don't get as much of this performance improvement, so that compared to the Gaussian, we still get the best performance for cold posterior with the Gaussian prior. Interestingly, if we introduce the correlations that we found, we can get an improved performance at all the different temperatures. So we get a generally better performance, but still the same cold posterior effect. So this suggests that at least in this case, the cold posterior effect and the performance are somewhat independent phenomena. So the take-home messages of this work are that the weights of SGD-trained neural networks follow heavy tail distributions and exhibit significant correlations, and that using these insights in the design of BNN priors can improve their performance and reduce the cold posterior effect. And with that, I'd like to thank all my amazing co-authors, and I'd like to thank you for watching.